So thank you, Tom, for the kind and generous introduction. I would also like to express my gratitude to the European Association of Geochemistry, the current president, Catherine Chauvel, and the FG Houtermans Award Committee for selecting me as this year's award recipient. I'm deeply humbled to receive such an honor. While this award is individual, the science and work environment that brought me here have been, in many ways, a collective effort. Therefore, I would like to sincerely thank the people who have supported my professional growth and contributed to my scientific achievements throughout my career. Tom has already done a wonderful job listing many of the people I wanted to acknowledge. I would like to start with Professor Zhang Zhu from the Chinese Academy of Geological Sciences, who introduced me to the world of isotope geochemistry and electric instruments. Then there's my PhD advisor, Arya, who is here today. Arya guided me to go further and beyond in the fields of isotope geochemistry and biogeochemistry. He's an outstanding PhD advisor. When I arrived in the United States in 2014, it was my first time going abroad. During our first meeting in the summer of 2014, Arya told me, "This is your PhD, not mine. You can choose to do whatever you want, and my responsibility is to support you." He gave me a lot of freedom to pursue my own research and trained me to become an independent researcher during my PhD. I'd also like to thank Laura Planaski at Yale and Ty Stoll at the University of Copenhagen, both of whom are exceptional postdoc advisors. They followed Arya's approach, gave me the freedom to work on my own ideas, and supported me as I explored isotopes beyond uranium and samples beyond ancient rocks. Next, I want to thank Professor Zhang from Nanjing University, whom I consider a significant mentor. In ancient Chinese, there's a saying, there are many swift horses, but very few who can sport them. I met Zhang in the summer of 2018 in New Haven when I was a postdoc at Yale with Laura Planaski. And he asked if I wanted to return to China to establish my own lab. At that time, I hadn't made a decision, but he traveled to Copenhagen to discuss the idea with me again when I was a postdoc there with Ty Stoll. Zhang is a sedimentologist and a paleontologist, while I'm a geochemist, a perfect match. We share many common research interests. I returned to China in late 2019 to early 2020, and with Zhang's help, I established my own lab, which Tom mentioned earlier. Since then, I've met many great people in China who have encouraged and supported me. Some of them are actually in the conference room, like Shui Chang, Quan Youchao, Jiu Bin, and Xiaomei. They're all here today. It's impossible to list everyone, but I must mention a few others, like Yigang Xu at the Guangzhou Institute of Geochemistry, Shu Chenxie at the China University of Geosciences in Wuhan, Hai Chen at Xi'an Jiaotong University, Shu Haixiao at the Regilia Tech, and Tom Ergio at the University of Cincinnati. I'm also fortunate to work with some talented colleagues and students in my lab in Nanjing. Now, I want to talk about the type of science I'm passionate about. I'm a fan of collaboration, and my passion is integrating geochemistry, paleontology, and Earth system modeling to quantitatively understand the evolution of Earth's habitability, past, present, and future. As Tom mentioned, this ambition is vast, but I'm fortunate to have a group of wonderful collaborators. Although I don't have time to list each of you here, you know who you are. I conclude by thanking my family, who have been an everlasting source of care and support. I come from a less developed area in China, and I was the first in my family to attend the university. My parents did everything they could to support me through my studies and beyond. Similarly, my wife and child now do everything they can to support my career. Let me share a funny story to conclude my acceptance. My wife once asked me to buy some meat for lunch, and I took it to my office because I forgot to go home. When I finally got home in the evening, the meat in the car had gone bad, and my wife and the child were just smiling at me and said, "Okay, we are eating isotopes today." Thank you for all your attention. I hope you enjoy the lecture that follows. Is there a laser point somewhere? Probably no. Do you have a laser? Okay, so I'll just get started here. So the screen is far away from me, so I can only stand here. So my lecture today focuses on the environment backdrop leading to the end-Permian mass extinction. Well, you know, so the end-Permian mass extinction provides a pretty good geologic analog to think about how Earth's biodiversity responds to rapid CO2 injections into the atmosphere ocean system. I will follow this outline and start by introducing some concepts about what we already know about end-Permian mass extinction. This is a pretty old figure summarizing the biodiversity change over the Phanerozoic and the big five mass extinctions. As you can see, well, I don't have laser, so I can't point. As you can see, so the end-Permian witnessed the largest mass extinction event in Earth's history. Yeah. Okay. Okay. Oh, thanks. Okay. Thank you so much. Oh. Yeah, seems does not work. Yeah, it's fine. Yeah. It's fine. I can just use this. So as you can see, so the end-Permian witnessed the largest mass extinction event in Earth's history. This is an updated high-resolution biodiversity curve over the Paleozoic. And although the data are from China, as you can see from everywhere in China, they mirror global trends. As you can see, so there was a sudden decrease in biodiversity during the end of Permian, which led to the losses of over 81% of marine and 89% of terrestrial species. I'm sure, so you know, many marine species, such as the brachiopods, fusilli, and corals, went extinct during the end-Permian mass extinction. Similarly, before the extinction, we saw flourishing tropical rainforest, but after the extinction, as you can see from the figure, so the collapse of the terrestrial ecosystem. So when talking about extinction, we first want to know the timing, when the extinction occurred and how fast it happened, right? So this is an outcrop at the Meishan GSSP section, and the extinction occurred between bed 24 and bed 27. So there are several beds, as you can see, there are at least 2 ash beds, so which provide some critical age information. So based on the high precision ID teams uranium net dating from the Meishan GSSP section, where we know, so the extinction occurred between bed 24E to bed 27, so which is within 61,000 years, so which is a sudden event in the geologic history. So this is a nice summary figure from Nanjing listing all the significant volcanic eruptions we know today. So we know the end-Permian mass extinction was related to the volcanism. So when compared to the Siberia traps, all those eruptions are way too small, as you can see. So this is the Siberia trap. These are all the major eruptions we know today. So except for the Siberia trap large igneous province, so I want to mention that recent studies from our group also call upon the volcanism surrounding the Texas region. As you can see, so there are many like volcanic records surrounding the Texas region. And there are still debates on the Siberia trap versus volcanism surrounding the Texas region as a direct cause of the extinction event. We also know, so there was a rapid increase in sea surface temperature, and this is counted with appetite oxygenative records from the Meishan GSSP section. And we can see that the temperature rise across the end-Permian mass extinction at the Meishan GSSP, as you can see, so it's behind the onset of the extinction by about 23,000 years. And so there's debate on the role of warming in the extinction. There's pretty robust evidence from uranium isotope records and other geochemical proxies that the global expansion of modern alloxia occurred immediately before the EPME. As you can see, so the elective shift in uranium isotopes occurred right at the extinction horizon. The lithium isotope records also indicate a large drop towards low lithium isotope values across the end-Permian extinction, as you can see. So for both records, you can see like a large drop in lithium isotope records. But the interpretation of this negative security has been argued between chemical weathering and reverse weathering. So to summarize, we already know a lot. So we know the timing, volcanism, alloxial, high sea surface temperature, and changes in weather regions. But the problem is we still don't know the approximate killing mechanism, the relative contributions, importance of each environmental factor, and the interactions. So to move forward and think the Permian Triassic as a cistern, those are some of the most important environmental factors that we have to think about. So to start with the volcanism, which is typically related to the Earth's deep processes, which affects continental weathering, which in return changes atmospheric composition and regulate marine redox states. At the same time, so continental weathering also deliver nutrients to the ocean and regulates marine primary productivity, and all those factors will eventually influence or impact the biotic response. So here I'm going to use a lithium isotope to reconstruct changes in continental weathering, using uranium isotope to track changes in marine redox conditions, and using barium isotopes to track changes in marine productivity, and then think about how our system evolved during the Permian Triassic. The talk will emphasize multiple geochemical proxy, multiple geological sections, the same field of samples, but the talk won't go too much into the Earth system modeling because the data are pretty new, so we haven't had a chance to summarize the modeling results. But I want to emphasize that the integration of geochemical proxy data with Earth system models is very important. In the second part, I will talk about what we know about lithium, barium, and uranium isotope systematics in boron carbonates before running into the Permian Triassic story. Although this part is a little bit oversimplified simplified due to the limited time, but I think it's very important for us to know what carbonates can tell us about lithium, barium, and uranium before we tell geological stories. I will report all three isotopes using traditional data notation in this talk. I'm sure you won't have problem with this because this is Goldsmith, so I don't need to run into the details. To start with barium, so the basis of barium isotope as a productivity proxy, I think we can just get through from these two figures is based on the fact that so barium has a nutrient-like vertical profile with moderate depleted concentration found at the surface, as you can see in the surface, and various increasing to a deep maximum. And the other supporting evidence is that the barite accumulation rate is positively correlated with the downward flux of organic matter. So this foundation make barium and its isotopes as a productivity proxy. I want to spend a little bit of time to introduce this figure because this is kind of important for our interpretation later. So this is a simplified figure summarizing the biogeochemical cycle of barium in the ocean. With the increase in marine productivity in the surface, more barium were incorporated into or absorbed into the organic matter, will be transported from the, you can see, from the surface ocean to the deep ocean, and in the deep water. So the barite precipitation from seawater is typically associated with a fractionation factor of minus 0.4 to minus 0.5 per mil. But the barite dissolution in deep water is likely associated with a negligible isotopic fractionation. That means, so the higher the productivity in the surface ocean, you will see heavy barium isotope composition in the surface water. And changes in surface water, barium isotopes can be recorded by marine carbonates. This is a laboratory experiment, as you can see, so which demonstrates that the barium isotope fractionation during wheatwright precipitation is almost negligible at equilibrium. It's only as you can see, so at isotopic equilibrium, the fractionation is only minus 0.09, so which is almost the electric uncertainty in most of the laboratories. So we have measured barium isotopic composition in two pusher cores from the South China Sea. So our goal is to examine whether those carbonates can feasibly record the barium isotopic composition of seawater. As you can see, so the two push cores, they are coupled in mass. They haven't become rocks yet. So they haven't undergone diogenesis. and they're very clean and white in color. So they can tell us whether we can use carbonates as archive for the seawater barrier isotope composition. So these are the results, as you can see. So there's pretty much a low radical variation in both push cores. So our results suggest that the carbonates can record the variation in seawater barrier isotope composition, and as you can see from the figure, there's almost no variation across depths. However, so if we accept a surface seawater barrier isotope composition of minus 0.59, so this is a real merit from the South China Sea. So we see there's an offset between carbonates and seawater. So the two push cores are offset somewhere by minus 0.21 per meter between these carbonates and the overlying seawater. So this offset is likely controlled by carbonate mineralogy, not diagenesis, because as what we introduced before. So those carbonate mass, they haven't undergone those kind of diagenesis. It's only deposited in the past 500 years. So we can do a sample mass balance calculation to confirm that this is controlled by the mineralogy. And as you can see, so there's offset of minus 0.13 plus minus 112, between high manganese calcite and seawater. We then use two deep drill cores from the South China Sea, the two deep drill cores, one from Xisha Island and the other from Nansha Island, as you can see from here. So to examine the diagenetic effects on barrier isotope fractionation in marine carbonates. So the two cores are from South China Sea and have accumulated linearly. So you can see that two deep drill cores, and they have accumulated nearly 100 meters of carbonates. As you can see from the mineralogy and carbon and oxygen isotopes, so the two cores have experienced nearly all typical carbonate diagenesis, as you can see. So it's very characteristic, with different kind of diagenesis. So the sedimentation rate in the South China Sea is also significantly higher than that in the Bahamas. So that means we can get a little more information about diagenesis from the South China Sea than in the Bahamas. Those are the results from the Shiko drill core. So we measured the top 600 meters in the core. You can see, so I plotted carbon, oxygen bearing, and their concentration there. So what you can see, so there's some variation in barrier isotopes, but overall, so the variation is quite small and it's likely controlled by carbonate mineralogy, as what we introduced before. And this is the result of the Lanke drill core, which is consistent with the Shiko drill core, where you can see, so it's very easy to identify different kind of diagenesis based on carbon and oxygen isotopes, also like mineralogy. And the two cores, I don't have time to run into the detailed interpretation because time limitation, but the message from the two deep drill core from the South China Sea is that it seems that the diagenesis has a very limited impact on carbonate barrier isotopes. Or run into this nature. We haven't run any reactive trace model modeling to understand a little bit detail, but I think we'll do this later. So this is a summary. This is a figure summarizing the modern oceanic lithium cycle. So I realized that there are more than 20 talks related to the lithium isotopes on Monday and Tuesday, and more than 5 of them have introduced this figure before, so I'm going to skip it. Instead, I'm going to focus on what we know about lithium diagenesis in the South China Sea. This is a frontiers paper from EPS written by myself and Guang Yi. I think Guang Yi is also here today, this year. And we compared the diagenesis between the South China Sea and the Bahamas and some other carbonate settings, as you can see. So these are basically the diagenesis from global localities. So we measured lithium isotope for the cores. Those are the cores, the two push cores, and the Shiko drill core. So this is the long drill core. We want to use the core and the push core to understand whether carbonates can recoil seawater, and use the deep drill core to understand the diagenesis on the carbonate barrier isotopes. So So the cores tell us that, as you can see, so the isotope composition of cores, they are lower than the abiotic electrolyte, demonstrating there are some right effects on lithium isotopes. And for the shallow push cores, which are comprised of abiotic, as you can see from the carbon mineralogy, they're comprised of abiotic electrolytes and high manganese calcites. And their isotope composition are consistent with the mineralogical control. But when you look at the deep drill core, so these are the lithium. I know, so the screen is a little bit small, so I'm not sure whether you can see this. So the deep drill core is comprised of low manganese calcite and dolomite, and you can see there are large variations in lithium isotopes. So these are not related to seawater. So I'm sure. So we know this is related to controlled by only diagenesis. So the lithium isotope data from forward have been argued. So this red line is a forward records. So which has been argued to represent the primary seawater cycle during the Cenozoic. And when compare our lithium isotope records with forward, so we can find that the lithium isotope of samples that underwent Moran diagenesis, as you can see, for the Moran diagenesis and dolomitization, they are very close to the forward, so which means they record seawater. But for lithium isotope of samples that underwent meteoric diagenesis, this blue area, as you can see, they are like apparently there's some offset, they are lower than seawater, but very close to the primary minerals. So which means that so we're running into this letter. So about the counting factors. So when comparing the lithium dielectric pattern from the South China Sea, so this is from the South China Sea, this is from the Bahamas, and we see so the dielectric pattern are very similar, but the data from South China Sea provide much more details to understand the diagenesis of lithium isotope. This is a further comparison between the South China Sea, as you can see, the black, and the Bahamas, the red. So samples underwent the same type of diagenesis, so like weak diagenesis, meteoric diagenesis, and Moran diagenesis are very similar between different localities. We run a very simple reactive transport model, so we can further draw some conclusion that the lithium isotope of Moran carbonates depends on fluid composition and dielectric conditions. As you can see, so those are samples undergoing Moran diagenesis. These are like primary carbonates. They haven't undergone any diagenesis. Those are samples undergoing meteoric diagenesis. So samples that underwent Moran diagenesis belong to fluid buffer condition, while seawater has very low, so seawater has high lithium concentration. So samples that underwent Moran diagenesis have very similar isotope composition compared to the overlying seawater, which are those group of samples. But meteoric waters have low lithium concentration, and samples that underwent meteoric diagenesis belong to sediment buffer condition, as you can see. So their isotope composition are very similar to the primary carbon minerals. And so the third proxy is I will have like a 3 or 4 PowerPoint to very quickly go over this. So now the uranium has become a pretty traditional isotope system after like more than 10 years of development. So the reason why we use uranium as a redox proxy is because so uranium has 2 valence states that are stable in nature. So uranium 6 is soluble in oxygen water, and uranium 4 is sparsely soluble in seawater. And the reduction of uranium 6 to uranium 4 is associated with a large isotopic fractionation. So during periods of enhanced marine alloxia or expansion of oceanic alloxia, so more like uranium 6 will be reduced to uranium 4, and which will remove heavy isotopes from seawater, as you can see. So the seawater become isotopically lighter. I'm quickly summarizing what we observed from the South China Sea based on the 2 deep drill cores in order to keep my talk within the required time. So these are also the 2 cores we have studied for uranium isotope in the South China Sea, the long deep drill core, like about 1,000 meters, and that core we only studied the upper 600 meters. Those are the results from the South China Sea. So you can see the carbon oxygen, the uranium concentration, the isotopes from the Xike drill core, and also the uranium concentration and isotopes from the Lanko drill core. So the 2 lines represent the seawater composition, as you can see. So almost the low samples, they record seawater composition. and which is similar to this observed from the Bahamas. So when we plot the data from South China Sea and Bahama, so when we put them in the same plot, as you can see, so they're very similar, and this confirms that. So we have to apply diagenetic corrections for geological samples to reconstruct seawater values. But the key message, what I want to emphasize there is that we provide a pretty compelling result that the positive offset, as what we talked in the previous slide, is caused by the enrichment of isotopically heavy uranium-4 species in carbonates. As you can see, so there's very good linear relationship between uranium-4 over total U in carbonates and the uranium isotopic compositions. So which means we provide direct evidence to confirm that this is caused by uranium-6 enrichment. And this provides a means to robustly reconstruct seawater U isotope compositions through geologic timescale. So I think with those understandings from the South China Sea and the Bahamas, I think we should feel comfortable using U isotopes to track rate exchange, and barium isotope to track productivity, and lithium isotope to track changes in weather region. And so now let's go back to the Permian Triassic story and see what the uranium, barium, and lithium records inform us about the environment backdrop leading to the end-Permian mass extinction. These are our study sections. So our study sections include the Dajiang section in Guizhou province, and the Meishan GSSP sections from South China, and also the Abdan section from Iran. So basically, we have sections from different localities that are widely separated. I'm not going to dig into the very details, but just quickly go over our findings from these new studies. So here are the uranium isotope results, as we can see. So this is the uranium isotope result from the Meishan. This is the uranium isotope result from Dajiang. This is from Abdan in Iran. As we can see, so all those three sections show nearly identical active excursion, which coinciding with the extinction horizon. So this suggests that the rapid expansion of ocean along there occurred right at the extinction horizon. So which means, so probably ocean along there was likely the proximate kinematic for the marine species during the end-Permian. Let's take a look at the barium isotope data. So those are the barium isotope result from the Meishan GSSP section. We can see, so there's a rapid positive excursion in barium isotopes followed by a negative excursion afterwards. So when we compare the two records, the barium and the uranium isotope records, we can clearly see that the positive excursion in barium isotopes occurs before that of the negative excursion in uranium isotopes. So which suggests that enhance the marine biological carbon pump, because as what we introduced before, so this positive excursion in barium isotope is likely interpreted as enhanced the biological carbon pump in the Permian Triassic Ocean. So which means, so it's very likely that the enhanced biological carbon pump played a key role in triggering the global expansion of Loxia in the late Permian. And these are the barium isotope results from the Dajiang section, which is nearly identical to that of Meishan, as you can see. So the carbon isotope is very easy to align different sections because we have high biostratigraphic data. We have carbon isotope. We also have some absolute ages. So as you can see, that for the two sections, we also see a positive excursion followed by a negative excursion in the Dajiang section. So the two sections are separated by about more than 2,000 kilometers. And this is a comparison between barium and the uranium isotope records in three widely separated sections. So the two sections from South China, and this one is the GSFT, and this one is from Iran. As you can see, so for all three sections, the barium isotope are nearly the same. So we see positive excursion followed by negative excursion, and both uranium and barium, they are pretty much similar. So both uranium and barium isotope trends are likely globally consistent, and the trends are suggested to represent seawater cycle rather than cycle related to diagenesis. And the red arrow marks the onset of the positive barrel isotope excursion. As we can see that they occur pretty much consistent everywhere surrounding the TCS ocean. So when plotting the data versus geological time, we can clearly see that the timing onset of barrier. So this is barrier, this is uranium. So the timing onset of the positive barrier isotope excursion predates the end-Permian mass extinction horizon. So which is this this dashed red line, and also predates the elective excursion in uranium isotopes. So the detailed comparison between the two records with the extinction horizon argue that so it's very likely enhanced biological carbon pump in the ocean played a critical role in triggering the ocean alox in the latest Permian. And also there are several talks about modeling who argue for warming as an important trigger. But I want to call attention that so we should also think about the productivity change in the Permian Triassic oceans. And for continental wetlands studies, we analyzed the high-resolution lithium isotope in 3 widely separated carbon sections. As you can see, so we analyzed the Nanjing section in South China, the Abadan section in Iran, and the GK1 drill core in Austria. So the reason why we haven't done the Meishan GSSP section is we believe this is not a very good section for lithium isotope study because the carbon content in that section is pretty low. So when you use a sequential dissolution for that section, it's very easy for you to get some contamination. So we just get rid of the Meishan GSSP section. So we focus on 3 very good carbonate sections. So we haven't examined the Meishan as what I told you before, but we found consistently elective lithium isotopic composition. So the middle line is lithium. This is lithium from the Iran. This is lithium from Austria. As you can see, so we pretty much found consistent elective excursion across the Permian Triassic boundary. As you can see, the elective excursion in almost everywhere globally. So the lithium isotope excursion across the Permian Triassic boundary decreasing from 20 per million in the late Permian to about 10 per million during the Permian Triassic boundary, and then recovering to something 50 per million in the earliest Triassic. So there's a large drop in lithium isotope composition during the Permian Triassic transition. So we compile carbon, lithium, oxygen, and uranium isotope data. So we can find that the onset of the lithium. So this one the lithium isotope records. So which is prior to the end-Permian mass extinction horizon, which is represented by this line. But lithium is later than those of carbon and uranium when you compare the elective maximum between different kind of records. So we believe this may reflect a reservoir effect for lithium in the global ocean, as lithium has quite a long residence time than carbon and uranium in the ocean. So we also lithium has a residence time of a few million years, and uranium has a residence time of less than 0.5 million years. So there are many factors that can affect the lithium isotope records in carbonates, such as seawater pH and temperature. So there are pretty good laboratory constraints on those factors. So based on those laboratory experience, the pH dependent, the temperature dependent fractionation. So we think the changes in seawater pH and temperature during the PD boundary cannot lead to such a large as the 10 per mil elective excursion during the Permian Triassic boundary. So as for only diagenesis, as what we learned from the South China Sea and the Bahamas, so we know the marine barrier diagenesis is dominated by a seawater buffer condition. So which means the 3 shallow water sections we studied can be used to directly document the colloidal seawater information at the time. So seawater temperature can also affect the lithium isotope fractionation during removal into the global ocean. So the 2 most important factors we care about is the oceanic clay formation and the oceanic crust alteration. But based on this irradiation from the irradiation of seawater change during the Permian Triassic, so we find that, and based on this theoretical study, So we find that only about 3 per meter kept data lithium decrease is driven by climate change is only Triassic, but our observation is like almost 10 per meter. So all these factors can't interpret our data. And this is a very classical plot that basically everyone will use. So based on the frameworks of the modern real-world lithium systems, so decreased seawater lithium isotope composition can be very low. So both like low WD ratio and high WD ratio, where you can generate like very low lithium isotope composition. So here, so the WD ratio is defined. Is defined by the ratio of chemical weathering to total degradation rate. And at the same time, so we can also take a look at this figure. So the WD ratio versus dissolved lithium yield in the water. So we can also observe a linear lective excursion between WD ratio and the real lithium flux. So which means only a lower WD ratio corresponds to like a high real lithium flux. So with these basic understandings, so we can use like a very simplified box model to reproduce seawater lithium isotope change during the PT boundary. So based on, so we test 3 different kinds of situations. So the first situation is we test like low weather intensity but high denudation rate. And in this case, we just keep like the isotope composition of river constant, but we change the flux. And in the second scenario, we test like high weather intensity but low denudation rate. And in this case, we just lower the lithium flux to the ocean. And in the third scenario, only increase in lithium flux, reflecting low weathering change, and only increase in the runoff. So we suggest that, as you can see from different curves, if you want to like produce a 10 Permian active excursion, and I think the most, or probably the only like solution is just change the chemical weather intensity, which means we have to drive by decrease the chemical weather intensity and less detrital cliff formation at that time. As for the causes of the lower chemical weather intensity, we propose that the terrestrial system collapsed before the marine extinction. So there are a lot of publications from like in the past 5 years which argue that the extinction on the land like occurred before that in the ocean. So this kind of the differences in the extinction between like land and ocean so can led to significant decrease in chemical weather intensity and less detrital cliff formation because you don't have plants on land. And as a consequence of changes in chemical weathering, so we suggest that decreased cliff formation may lead to more like phosphorus delivered to the ocean. And at the same time, you can also like lower organic carbon barrier efficiency in the ocean. So all these factors will contribute to the expansion of alloxia. So back to the take-home message. So we provide a diagenetic framework for lithium barium and uranium isotope systematics in modern carbonates based on drill cores from the South China Sea. And lithium barium uranium isotope from 3 widely spaced sections are nearly identical, demonstrating their primary nature as a global seawater cycle. And then we have some detailed comparisons between the 3 isotope systems. So we get a little bit more details about internal interactions. So I'm not going to like read all the texts. I will stop there. So thank you for your attention, and I'll be happy to take questions. I know so the talk is a little bit simplified, very low. So a lot of details I just don't have time to expand. So if you have any time, just feel free to contact me through email, or if you have like additional source on this lecture. So I'll just stop here. I think I have a few minutes. If you don't have questions, then feel free to email me. So here's my email address. Just feel free to email if you want to discuss anything about the talk. So thank you. Yeah, thanks.